Hi class, welcome back to Electromagnetics. So today we're going to talk a little bit about line integrals as I mean to make sure we understand this. Hopefully you've had this in calculus before, so this will be a little bit of a review, but we're going to go beyond the review and start to show how we use this and utilize this with electric fields in electromagnetics. Thought for the day, Proverbs 3:5 through 6. Very common verse. Trust in the Lord with all your heart and lean not on your own understanding. In all your ways submit to him, and he will make your path straight. So I thought this was an applicable Bible verse because as we talk about line integrals, we are going to be talking about going along the path of a line and integrating that and setting that straight so that so we can evaluate the integrals correctly. But nonetheless, we should trust in the Lord with all that we do and lean not on our own understandings. There are many things that we don't understand in life and in engineering, and we need to trust Him in that. So this officially starts part 2 of the course. So the homework sets will now be a different set. As you can see, we're going to talk about and do a little bit of review on line integrals and surface integrals, although those will be both beyond review because we'll start to show how we utilize those when dealing with electromagnetics. But then we also, the last 4 lectures are going to introduce Maxwell's equations. So just some things to keep in mind before we jump into this. Maxwell's equations come in 2 forms. So when we deal with them in the integral form, these forms govern the interdependence of certain field and source quantities associated with regions in space. That is, contours, surfaces, and volumes. So it's kind of a macro application of these equations. Conversely, Maxwell's equations in differential form relate to the characteristics of the field vectors at a given point to one another and to source densities at that point. So this is kind of the micro approach or application of these equations. But we want to look at both of them because they both have their uses and applications. So we want to understand. We want to understand more than just the math. We're definitely going to look at the mathematical formulation, but I want to really press on you to understand the physical significance, to kind of get a feel for what this is telling us, and maybe give us some intuition about how electromagnetics work in real life. So the integral forms of these equations deal with the field quantities, line and surface integrals of electric and magnetic fields. So that's why we want to go ahead and review that now. So to set up our discussion here, initially we want to consider a test charge. So we'll just call this lowercase q. And we're going to consider it in the presence of an electric field, E. And the test charge we're going to say is going to move along this path C. And we're going to go from point A to point B in the presence of this field. So as we consider this, we want, the path itself could take any shape, any curve, or anything like that. It's not necessarily a straight line. So because of that, we want to divide this path up into infinitesimally small segments. So we're going to chop it up into these segments. And so these are the delta L's. So I know that's a little confusing. There's not an I, that's an L. So we have these delta L's, 1, 2, 3, J, all the way out to N. And so each one of these vectors, now these are vectors, so they have a length, a magnitude length associated with them. They also have a direction, so they're always pointing in the path, in the direction of the path. So that's important. So that being the case, we can now define an angle alpha for each one of these. It shows the difference between the direction of the path vector and the E field vector. So we have this alpha for each one of these. So being that we have this defined now, we can express the work done, or that would be required to move this test charge Q along each segment as it moves along the path. So we'll have this delta Wj, so that's the incremental work for each little line segment. And so it's going to be our test charge Q. It's going to be the magnitude of the E field at that point, so the length of this vector, Ej. It's going to be the cosine of alpha, so the cosine of the angle for each one of these segments, and then the length that we're moving it, so this delta L. So this is standard definition for work that we're putting into play here. So now if we do this for all the segments and add them together, we then can derive this expression for the total work done moving the test charge along these points. So that's what we're indicating here. So we've got this work required to go from point A to point B, and so we've got the work for each one of those little segments, and we can add all those up. Of course, we can go back in and substitute the equation that we derived from the previous section for each segment, the amount of work done there, or we can utilize the summation notation from calculus as well. So we have the test charge, which is a constant for each jth length, or infinitesimal length. We've got the magnitude of the field at that point, the angle for each length between the field and the length vector, and then the magnitude of the length itself. But if we consider that this is the cosine of alpha, this is the definition of a dot product, right? So if we consider Ej with its direction and the delta length with its direction, we can just write the notation as a dot product here. So now we've created this expression for the work from A to B as this summation of these dot products. So if we continue to divide this path into smaller and smaller segments that are infinitesimally small until the number of the segments approaches infinity, of course the accuracy will continue to improve. We've learned this from calculus, the fundamental rule of calculus, so we can reach the state where we can just write this as an integral, right? So that's really what the integral sign means, is we're letting those segments continually get smaller and smaller. And so now we have this integral form of the equation to express the work. And again, this is the work required to move the charge from A to B. It's Q integrating from A to B, point A to point B of E dot dl. So this is a much cleaner notation and put into use our knowledge of calculus. So the integral on the right side of this equation then is known as the line integral of E from A to B. So that's the way we should learn to say this then. This is the line integral from A to B of the E field dotted with the length vector. So if we take this definition then and now divide both sides by the value of the test charge, that is, we just make this arbitrary, we then have the work per unit charge done by the field in moving the test charge from A to B. So if we do that, we define a new quantity here. This quantity is known as the voltage between A and B. And so this is probably a new way for you to think about voltage. Voltage is the potential difference. It's the potential to move a charge. Many times we think of Ohm's law, V equals IR, which you have moving charges already there. That's what the I is, the current. It's a moving charge. So in this case, in free space, we may not have a charge actually moving, but if we have a E field or electric field in place, then there's a potential to move a charge. And so we can quantify that now as a new way to express voltage. So the voltage potential between A and B is now the summation from A to B of the E field dotted with the length, that vector length of the path that we're considering. So if we think of this in other words, in the absence of any test charge, this value is the potential to move a charge if one were present. So that's why many times you hear voltage referred to as the potential difference. So So now if we extend this to consider a line integral for a vector around a closed path, as illustrated here, this is known as the circular of that vector. So again, we've got this E field coming across this space, and now we could just pick an arbitrary point here where my pointer is and say we want to, what's it going to take to move the charge all the way around and bring it back to the same place. And so we denote that then with this integral with a little circle around it. Maybe you've seen that, and we put the little C at the bottom. So this means we're integrating around the entire contour, or around the entire closed path. So if this is what we're doing, this is defined then, the voltage around the path, as the electromotive force. So maybe you've heard that term before, and maybe even thought of it in different terms, but when you're considering electromotive force, that means what's it take to move the charge all the way around this path and bring it back to where we started. So I want to look at some examples, but before I do, I want to reach back to calculus and maybe spark your memory just a little bit. There's going to be times when we're going to have to do a transformation of variables. And so what that means is if we have some function, which will be our electromagnetic field, and it'll have an x and a y component, remember the x and the y component could be defined in terms of time. That is, it's a time-varying field. So that being the case, we need to do a transformation of variables. So I just pulled this from a calculus book. So if we're going to integrate around this contour, x and y, and f at x, x and y are both functions of t, which is what this is saying here, we can substitute those definitions in terms of t, but we have to multiply by this factor here, which does a magnitude correction, is what it's doing. And so that's first derivative of x with respect to t squared, first derivative of y with respect to t squared, square root of that, and that changes our integral variable to t. So with that identity in our back pocket, hopefully that's sparked your memory a little bit. Let's look at an example of how this works. So let's say we wanted to evaluate this circular integral of x squared y ds, where c is determined by these parametric equations here. So x is defined as 3 cosine t, and y is defined as 3 sine t, and we're letting t go from 0 to pi over 2. Well, if we use that identity we just talked about, here's our original integral they ask us to evaluate. So here we put in x in terms of t, so it's 3 cosine t, which comes from right there, squared, because it's squared here, and then 3 sine t, and then we apply this factor as to do the transformation of variables. And so this is supposed to be the first derivative of x in terms of t. So 3 cosine t becomes minus 3 sine t when you take the derivative, squared. And then 3 sine t becomes 3 cosine t squared, square root dt. So we've done the transformation of variables there from x and y to t. We can then do some simplifications here using some trig identities. And so that becomes 81 from 0 to pi over 2. That's what's defined here, our range of integration. And so this now becomes cosine of t squared sine t dt, which, if we look at our integral trig identities, turns out to be gives us negative 81 over 3 cosine of t cubed from 0 to pi over 2. Plug the values in, and we should come up with 27. So if we evaluate this integral around this contour, we get the value of 27. So we can extend this identity to 3 dimensions, f of x, y, and z. It's just the exact same thing. We do f of x, t, y, t, z, t, and then we just add the zt term to this factor at the end of the square root. So let's consider another line integral example. In this case, we have this path given here, C1 and C2. C1 goes from O2 to 3,2, and C2 goes from 3.2 to 3.5. So x value goes from 0 to 3 here. We're already at 2, y equals 2, and then x stays constant at 3, and then we go from y equal 2 to y equal 5. And so they want us to integrate this along this path. So let's look at how we do that. So for C1, we know that y is going to equal to 2 all the time. Y stays constant. And so our dy, which is our change in y, is 0. Y does not change at all, so dy is equal to 0. So if we take that into consideration, we can take the integral of C1 of xy squared dy, xy squared dy. Well, remember dy is equal to 0, so this part drops out. So we're left with xy squared dx. Okay, and we know that y is equal to 2, so we can plug that in. So 2 squared is 4, and so that gives us 4x dx from 0 to 3. Of course, we integrate that, it gives us 2x squared evaluated from 0 to 3, so that's equal to 18. So that's the value for this first line segment here is 18. So now if we consider the second line segment, C2, we observe that x is equal to 3, right? X is 3 here, x is 3 here, so that means our change in x, or dx, is equal to 0. X does not change. So that being the case, this term now drops out to 0. So now we're just left with this term right here. And we know that x is equal to 3, so we can plug that in. That gives us, instead of xy squared, we get 3y squared. And so dy, so y is varying from 2 to 5, so that gives us our limits of integration, 3y squared. So we evaluate that, 3y squared is going to equal to y cubed, evaluated from 2 to 5 gives us 117. So then the total path integration, we just add those two together. 18 was for the first part, 117 was for the second part, so the grand total and solution of this problem is 135. All right, one more example we want to look at, and we're actually going to kind of look at this in a couple of different ways. And this one's kind of more applying some electromagnetic terminology to this. Let's consider an electric field given by E is equal to YAY. So that means as you move in the Y direction, the E field's pointing in the Y direction, and it increases the further you go up the Y axis. So we want to determine the work done by the field in carrying a charge. Now our charge is 3 microcoulombs, so 3 times 10 to the minus 6 coulombs of charge. And we want it to go from point A, which is down here, 0, 0, 0, our origin, to the point B, which is up here, 1, 1, 0. And we want it to travel along the path of y equals x squared. So it's going along this parabolic path. It's not going in a straight line. Again, we're following this curved parabolic path shown in 2.2. So the first way we want to do this is we want to divide this path up into 10 segments. So you can see they've done that here. So each one is the jth segment. So it travels a little bit of distance on each one of these j segments. And so they're kind of showing here that as we divide that up, we'll approximate the delta Lj by a straight line here. Divide the path up. So like I said, we're dividing into 10 segments, and so when we look at what our field is at each point, remember our field was defined on the previous page there. We get that E jth term is going to be j minus 1 squared times 0.1 ay. So this is our y value is what this is going to give us. Remember it was y a1, and since there's 10 segments, it'll be 0.01. So the length vector corresponding to these j segments, we can again approximate as a straight line. And so these delta Lj's are going to be 0.1 ax, so we're moving along the x-axis 0.1 at a time. And then it's going to be plus j squared minus j minus 1 squared. Remember, it's x equal y squared. 0.01 in the y direction. So we're moving over this much in the x, and then we're going up this much on the y. So if we do some simplification here, we see that our delta L will then be 0.1 AX plus 2J minus 1 times 0.01 AY. That's a straight line approximation, so it's not a parabolic, right? So this is defines our length and the direction. Remember, it's a vector. So we got the magnitude will give us the length if we took the magnitude of this, but we've got it written in this form so we can make sure and indicate the direction so that when we take the dot product, it'll work out correctly. So now that we've defined our E and our delta L's, we should be able to use our summation that we defined before, right, for work. So remember we said that the work going from A to B is equal to the summation of the charge times the dot product of each of these line segments, our EJ dotted with our delta LJ. And we divided into 10 sections, so it's from J equal 1 to 10. So if we start to plug in our definitions from the previous slide, remember our E was J minus 1 squared, which is just Y squared, 0.01Y. And then our length vector here, delta L, remember we're doing 0.1 in the X direction, and then 2J minus 1 times 0.01 in the Y direction. So these are our dot products. So here we can do the dots, and when we do, remember if we dot this first one, our AY and our AX, that one's going to fall out because the dot product of these two, they're perpendicular to each other, so the dot product would be 0. So then what we're left with is this AY dotted with AY, so it'll just be this quantity times this quantity, and that's what we see here. J1 squared, 2J minus 1, and so that falls out. So now if we apply this, we can let J go from 0 to 10, and that's what these are, and as we evaluate them, we get these 10 numbers. We can add those numbers up, and we should get 4,335, and we multiply that times 3 times 10 to the minus 10, and that works out to be about 1.3, a little more, 1.3005 microjoules. That's how much work is required if we consider this as 10 separate line segments all the way up. Of course, we can also work this as just a straight line integral. And so we want to illustrate that to see how these two compared. So to do this, we note that at any arbitrary point x, y, 0 on the curve, y equals x squared z equals 0, the infinitesimal length vector tangential to the curve then is given by this right here. So the dl, or the change in length, is going to be the change in x in the x direction plus the change in y in the y direction. Well, we already know the relationship between this, right? So x is equal to y squared, y is equal to x squared, excuse me. So if we substitute that in, y equal to x squared, we now come up with a new term as we take the derivative of this, right? The derivative of x squared is 2x dx. So now we have dx ax plus 2x dx ay. So this is handy because now we have our differential length defined in terms of just x only. We still have a y direction component, but the variables are all in x. So the value then of E dot dl at the point yx0 is yax, this was defined at the beginning of the problem, dotted with this new definition here. Well, originally it's dx ax dy ay, but we substitute our new expression in for this. And then also for y, we know that y is equal to x squared. So then this goes to x squared ay dx ax plus 2x dx ay. So again, we have this dot product now expressed in a single equation that's only variable is x. And so again, if we take the dot product, this ay ax part drops out completely because they are perpendicular with each other. So now we're just left with this ay and this ay term dotted together. And when we do, we have 2x and x squared. That gives us 2x cubed dx. So now we can go back to our integral form. Remember our definition was the work from a to b is q, the charge integrated from a to b E dot dl. Well, the charge was 3 times 10 to the negative 6, a microcoulomb. We're going from 0, 0, 0 to 1, 1, 0. But now our E dot dl, we've now simplified this down to just be 2x cubed dx. So now if we just do the integration on this, 2x cubed, the integral of that is 2x to the 4th over 4. The only variable we're concerned about is x, so that goes from 0 to 1. Plug in the values, and we come up with 1.5 microjoules. So if we remember before, when we evaluated as line segments, we got 1.3 microjoules, and that's just an approximation, whereas here this should be exact. So you can see it's pretty close, and if we were to keep dividing that up, so instead of 10 segments, say 100 segments, and then 1,000 segments, that answer would approach this answer, which we know from calculus this one is exact. Let's look at one more example of doing a closed line contour integral. They want to consider a force field. Again, this could be any force field, but it's defined as XAY. And so they want us to evaluate the contour integral of f dot dl, where again this closed path is we're going from A to B, B to C, C to D, and D to A here. So we want to evaluate this integral along that path. Well, when we're dealing with straight lines like this, usually the easiest thing to do is to break it up into however many number of integrals you need for the number of line segments you have. So we have 4 line segments here, so we'll have 4 integrals: A to B, B to C, C to D, and then D to A to get us back where we came from. So we can simplify each of these integrals pretty easily by looking at them separately. So for the first one, from going from A to B, we see that y is a constant at 1. As we move across here, y never changes. So dy would be 0. So in this case, dl then is going to be dx ax, and there's no change in the y direction, so it's just dx in the x direction. So now if we take this dot product, remembering that our f was xay and our dl is dx ax, these dot product is going to be 0 because these unit vectors are perpendicular to each other. So this first line segment is 0. If we consider now from B to C, we see that from B to C, x is not changing. X is 3 all the way through, so dx would be 0. So now our differential length, the x part's 0, the dy ay part comes there. So now if we take this dot product and evaluate that out, again, we have xay, but we know x is equal to 3, so that's where this 3 came from. So we have x3ay dotted with dyay. We're dotting 2 ays together, so that means we just multiply their magnitudes together, so that gives us 3 dy. So now we're integrating this, and y goes from 1 to 5. So we got 1 to 5, integral of 3. Work that out, it's pretty simple, and that comes out to 12. If we go from C to D, this is probably the trickiest one. We have to define y. Y is going to be 2 plus x, and that's just, we get that from the equation of a line here. Our dy is going to equal to dx in this case. So now we have that the differential length, dx ax plus dx ay. If we dot this out, remember we have our xay is our f, which is originally defined. Now we've got this dx ax plus dx ay, so that's going to give us x dx. Okay, and again, this is from the dot product, right? So our ay, ax, that part goes to 0 because they're perpendicular. So we're left with this dx ay and our xay, which that's where we get the x dx. And so when we integrate this, we're doing the change of x. So x changes from 3 to 1 here. So that's why we go from 3 to 1 of x dx. And when we evaluate that, we get -4. And then finally, from D to A, in this case, x is equal to 1. So our dx will be 0. Plug that back into our dl equation. Again, this ax term goes to 0. That leaves us with dy ay. So as we evaluate our f, since x is 1, we're only left with ay, and then we have dy, ay. Of course, the dot product of that is 1 and leaves us with dy. So if we integrate now, dy and y here goes from 3 to 1, so we're going from 3 to 1, and we get -2. So now we've done all 4 segments. From A to B was 0, from B to C was 12, from C to D was -4, and from D to A was -2. We add those up, and it gives us a result of 6. The total value is 6 for the entire path.